Hello, here we'll talk about eigenvalues and eigenvectors. Actually, eigenvectors come first. Eigenvalues are derived from eigenvectors, but yeah, let's start with the beginning. At the beginning, there is a vector space and a linear map from the vector space V to itself. Such linear maps are called linear operators. What an eigenvector is a vector, and on 0, 1, because 0 will satisfy all the conditions imaginable. So a vector is called an eigenvector for the operator T. If the line it generates, so that will be the subspace of the vector space V of vectors which are proportional to this little vector V. If this subspace is preserved by the operator, so it is mapped to itself, or maybe something inside it. If it is a line, the only thing inside it is just the zero subspace, and that is a particular case of an eigenvector. So any solution of a homogeneous system corresponding to the linear operator V is an eigenvector. But in general, we are just asking for this line in the vector space on which T operates to be preserved, to be changed inside, but as a whole, as a subspace, to be preserved. So let's look inside. Let's see what happens inside this line which T preserves. It's enough, because the line is all vectors all proportional to one vector V. It's enough to see what happens to this vector V. And the vector V has to land somewhere in the line, so it has to be proportional to itself, or other, the image under T of V has to be proportional to V. The proportionality coefficient is called the eigenvalue of V. And this number C, that's what is called eigenvalues. So collection of all of them is called the spectrum. Just all the numbers which appear as solutions of this equation. So C is called an eigenvalue if there is a vector which is not 0 and which is stretched with the coefficient C under this operator. So just from the definition, just not knowing much about the these eigenvalues, just from the definition, we could see some basic properties. So, for example, if C is an eigenvalue, so I'll be writing it as C belonging to the spectrum of T. Then we could be sure that C squared will be in the spectrum of T squared, T composed with itself. And that is just from the very definition. So the vector, which will be the eigenvector for T squared with this eigenvalue, will be the same vector V, which makes C an eigenvalue of T. So that is a straightforward property, because T squared applied to vector V will be like T 2 times applied to vector V. Once applied, V is scaled, T is linear, and then we can apply T again and write the eigenvalue equation for T of V. That is C times V, and then we have 2 C's as a result, so we have C squared times V, making V an eigenvector for T squared with a different eigenvalue, C squared. The same way we can prove that, say, 5 times C is an eigenvalue of 5 times T. So we can multiply operators by numbers, and that is what 5 times t is the operator which does t, whatever t does, and then scales it by 5. And then the eigenvalue, the number 5 times c will be the eigenvalue of that. The proof is totally identical. So more general statement would be just take any polynomial. If our field of scalars, if our numbers are real numbers, so take a polynomial with real numbers. And then the fact that c is an eigenvalue of t will make f, so that polynomial with c substituted into it, will make it an eigenvalue of f of t. We can take an operator and use f, the polynomial f, as an instruction, as a recipe to a sequence of algebraic operations. Compute some powers of t, multiply them by coefficients of f, take the sum of those monomials, and that will be a new operator, and then we can look at its eigenvalues, and f of c will be one of them. So that is a generic statement which is very convenient for computations. But let's go back to the general story of eigenvectors. Why we are interested in such subspaces and such vectors will be explained later, but here we will just look at how to find eigenvectors and their eigenvalues. And now the story turns around, so we were to start with eigenvectors, defining them, and then eigenvalues come second. In computing, we will have to find eigenvalues first. Computations are done effectively with operators written in matrix form. That is, we are assuming that our vector space is a coordinate vector space, and then an operator we're looking at is really a multiplication by some matrix M. So this matrix will be of square size n. And then the equation, this equation we are solving to find eigenvectors and the eigenvalues becomes a matrix multiplication of m with a vector being equal to the same vector proportional with some coefficient. Alternatively, we can write this equation as a homogeneous equation if we just take the right-hand side and subtract it from the left and use matrix multiplication properties. We can write it like that. Matrix M, our operator matrix, minus identity matrix times that eigenvalue number, as a square matrix multiplied with vector v gives us 0. That is an easier way of writing the equation. It might not look like, but the point is that now this matrix, we don't know v and we don't know c, so we have too many unknowns, but now we know something concrete about this matrix. It has a non-zero vector, v has to be non-zero from the start. It has a non-zero solution in the homogeneous system, so such matrices are called degenerate or singular. And what determines them is, what singles them out, what determines if the matrix is degenerate is the determinant. So now we have an easy recipe of how to see that such situation is possible at all. This matrix has to have 0 determinant. And now we only have one unknown, so we are now to find those numbers such that if we multiply them by the identity and subtract from our matrix M, the result will be with 0 determinant. So we could just keep this unknown c a parameter, a variable, and write an equation that the determinant of M minus this unknown t times identity is 0. And that is called a characteristic equation. And this quantity, the determinant of m minus t times identity, is called the characteristic polynomial, because if we look what it gives us as a function of t, it will be a polynomial function. And the fact that it is a polynomial function comes from the definition of the determinant. The determinant is a certain sum of products of matrix entries. The sum of these matrix entries will have t in them, so it will not be pure numbers. And then as a result, we will have some polynomial expression as sum of products of linear terms and numbers. So that's how we find first solutions of this equation. Characteristic equation solutions are also roots of the characteristic polynomial, and they are these eigenvalues. The spectrum is to be found first. The spectrum now of the matrix of our operator is just the set. Reformulating the condition here, the definition there is just a set of roots of the characteristic polynomial. And after we find these roots, we can then solve these equations for v being unknown. So as soon as we know which c's are good as eigenvalues, we can see what eigenvectors they have. And then it will be a sequence of homogeneous equations, one for each eigenvalue. So that is the strategy. Let's look at a simple example to illustrate it. Let's take an operator on a two-dimensional vector space given by this easy matrix of all ones. Then the first step is to compute its characteristic polynomial, and that is the determinant of the matrix from which we to subtract the identity times t. So that is just subtracting t from diagonal entries, because that's where non-zero entries of the identity matrix are. And then computing the determinant for 2 by 2 cases, just using the formula. We have 1 minus t squared, the product of diagonal terms, minus the product of off-diagonal terms, and then writing it as a polynomial, we have t squared, we have negative 2t, and then we have nothing, so the constant term cancels out. 1 squared minus 1 will give us 0. That is good because we can factorize this polynomial, easily find its roots, which are the eigenvalues of our matrix. And the eigenvalues are 0 and 2. So the spectrum of our matrix consists of 2 numbers, 0 and 2. And now to find eigenvectors with these eigenvalues, we have to solve this homogeneous system. So the first one for 0. We have to subtract 0 times identity, which is just nothing, which is just 0 matrix, from our matrix M, and that is just our matrix M. And then we have to solve a homogeneous system with this matrix. So I'll be just transforming with Gauss transformations this matrix to reduced row echelon form, and there's just one transformation of row subtraction, row 2 minus row 1, which gives the reduced row echelon form from the start. So the only equation we have between the coordinates is that the sum of coordinates is equal to 0. And one fundamental solution will have these coordinates. If we take the free variable, the second coordinate to be 1, the first coordinate will be negative 1. So all solutions are proportional to it. Eigenvalues with eigenvectors with eigenvalue 0 are all proportional to this. Then next and last is the story of eigenvalue 2. Now we have to subtract 2 from the diagonal of our matrix, and that will give us negative 1s on the diagonal and 1s off diagonal. And again, we have to use Gauss elimination to find homogeneous solutions of system of linear equations with this matrix. We have to solve this equation. this matrix equation. And again, it is possible. So that is actually a check-in point for eigenvalues. If they are found incorrectly, we will not see solutions. And as long as we are seeing solutions, eigenvalues are indeed eigenvalues. Eigenvalues are only possible when we have non-zero solutions, when we have eigenvectors. And we can check that if we take our matrix M and multiply it with this vector, we will have the 0, 0 vector. So we'll have one, the sum of coordinates is 0. So then here we can again eliminate very quickly using row addition this time. And we will be still left with only one equation, which we are supposed to. We have to have a zero row and at least 1 0 row at the end of row echelon reduction, because the matrix we are looking at has to be degenerate. And then the equation we have is that the difference of coordinates is 0, and any solution this time will be proportional to vector 1, 1. So these are the two eigenvectors for eigenvalues 0 and 2 correspondingly, and any other eigenvector will be proportional to either this one or that one. More examples will come later. See you then.